we are basically given just a single number here, and we want to determine whether this number is happy. So happy number in number theory is just a number that is defined by the following process. So basically take that number, which is assumed to be a positive integer, and generate another number out of it. That next number is going to be the sum of the squares of the digits of the earlier number that you had. And then you keep doing that. You take that next number and look at its digits and take the sum of their squares and generate the third number. And you keep doing that on and on and on. Now, if at any point you hit the number 1, let's say you start with a 1 or at some point a 1 is generated in that sequence, then it's going to stay 1 forever, right? Because if we take the sum of the squares of the digits of 1, that's just going to be 1 square, which is still 1. So once you reach a 1, you're going to stay at 1 forever. And if we are able to do that at any point, so let me see. Okay, let's take 86 for example. Suppose I start from the number 86. If n is 86, the next number that's going to be generated is going to be 8 square plus 6 squared, which is going to be 64 plus 36, which is 100. Right? It's 100. So the next number then that will be generated out of 100 will be 1 squared plus 0 squared plus 0 squared, which is going to be 1. Right? 1 squared plus 0 squared plus 0 squared. And then once you reach a 1, you'll stay there forever. So this makes 86 a happy number, because if you start from 86 and you apply this a couple of times, you reach 1 and then you stay at 1. Let's suppose n is 19. Then the next number that will be generated will be 1 squared plus 9 squared, which is 82. 81 plus 1. Then the next number that will be generated from 82 will be 8 squared plus 2 squared, which is 64 plus 4, which is 68. And then the next number that will be generated from that will be 6 squared plus 8 squared, which is 100. And again, once you reach 100, the next number will be 1. And then once you're at 1, you're trapped there. But it's not a bad thing to be trapped at 1. In fact, those are the numbers which are called as happy numbers, which end at a 1 when you do this on them. And a sad number or an unhappy number is one that doesn't end, that doesn't have a fate like that. So let's take n equal to 2 as an example. Let's see what happens when we do this to 2. We'll take all the digits of 2 and square them and add them up. So the first number that we get is going to be 2 squared, which is basically 4. The next number that will be generated will be 4 squared, which is 16. The next number that will be generated will be 1 squared plus 6 squared, which is 37. Then the next number that will be generated from that will be 3 squared plus 7 squared. So that's 9 plus 49, which is 58. Then the next number that will be generated from that will be 5 squared plus 8 squared, which is 25 plus 64, which seems to be 89. Then the next number that will be generated from 89 will be 8 squared plus 9 squared, which is 64 plus 81, which is 145. And then the next number that will be generated from that will be 1 squared plus 4 squared plus 5 squared. So that's 25 plus 16 plus 1, 25 plus 17, which is 42. And then the next number that will be generated from that will be 4 squared plus 2 squared, which is 16 plus 4, which is 20. And then the next number that will be generated from that will be 2 squared plus 0 squared, which is actually 4. And then once you reach 4, you basically follow the same sequence again. So if you notice the numbers that we have here, we have 2. We start from 2, but then we reach 4, then we reach 16, then we reach 37, 58, 89, 145, then 42, 20, then we come back to 4. Once you're back to 4, this just keeps continuing forever. So we don't get trapped at 1. We instead end up in a cycle around which we go, but because 1 is not part of that cycle, these numbers are considered to be sad numbers. They're not happy numbers. So what we want to do is to determine whether a given number is happy or sad. So, and the number could be any arbitrary integer. So basically what we are doing is we are starting from a number n. We are applying some transformation on it. Let's denote that transformation by a function called f. Then we apply a transformation on that function. Then we apply a transformation on that function. And so on. And the question is, does it end at a 1 or does it end in a longer cycle, not containing 1? Why must it have to end at a longer cycle not containing 1? Like, why is there no third fate? Why are these two the only possible fates for any number n? So if we look at the whole space of numbers, right, n here is any number from 1 to 2 to the power 31 minus 1. Right, this would be somewhere around 2 billion, roughly. So if we keep following this process, can we actually go forever along this path? 2 billion means how many digits would there be? 2 times 10 to the power 9. So maybe 9 more digits, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Roughly 9 or 10 digits. It doesn't matter how many precisely. But whatever they are, if we were to um, figure out, if you applied f, any function to a huge number like that, how big is that next number going to be? So this first digit could be maybe a 9, the second digit could be a 9, the third digit could be a 9. If you want to arrive at as large a number as possible after we apply the transformation, let's imagine all of these numbers to be 9. So we would have 9 squared plus 9 squared plus 9 squared, right? Maybe 9 or 10 times, right? I don't know how many times, let's say k times. K is 9 or 10, something like that. So that's going to be 81 times k, right? Where k is roughly 10, 9 or 10. So that means this value is going to be roughly 800 or so at the max. That is the largest you can ever get. Doesn't matter what number it is. And if it's like a smaller number, if it had fewer digits than 9 or 10, then obviously the value is going to be within 800. So that means if we keep continuing here forever, sooner or later, we are guaranteed that we are going to come back to an earlier number in the sequence. You can view it from the lens of the pigeonhole principle if you like, that there's only a finite number of numbers, right, within 800. And once you do this 800 times, you're guaranteed that some number is going to repeat in the sequence, which means a cycle is guaranteed. What we don't know is whether the cycle contains a 1, and if it contains a 1, it's going to only have a 1, or whether the cycle is a longer cycle like this. It doesn't contain a 1 and it goes through like a chain of different values which keep repeating. So take 30 seconds to think about this. And so we want to determine whether the number is happy or not. Now you might be wondering, what are the real world applications of this? Well, I don't think there are any real world applications of this, but number theory, I mean, people also do things just for the sake of their curiosity, right? So I believe this idea of happy numbers originally came about because some mathematician's daughter was posed that problem in her schools, uh, and so he was just curious about it. If you've attended my array floaters, you might remember we talked about this problem of pancake sorting, how that came about. Uh, Again, through some anecdote from a professor's life. So a bunch of these problems are there just because somebody found them interesting, and so you can think of them as puzzle problems, not necessarily having engineering applications. Right? Number theorists very often uh, don't care, and sometimes are even proud of the fact that uh, like you might remember from Hardy's, one of those anecdotes from Hardy's uh, writings, that he's proud that uh, the work he does has no practical applications, because in his time all the practical applications seem to be pertaining to military uh, applications during the World War, I think the first World War. So let's since we are talking about detecting cycles here, and there are basically two options only: either the cycle has a 1 forever, or which means it's a single element cycle, or it's a cycle that has multiple values. So we could detect a cycle, fact that we are in a cycle, by using the same Hare-Tortoise technique. And once we are in the cycle, we could just check whether the value that we are at is a 1 or not. If it's not a 1, then we know that um, it's a cycle containing many different numbers, which means the original number we started out from must be a sad number. And if we are at a 1, then the original number must be a happy number. So let's follow the same template. The hare. So in this case, there is no explicit data structure over which the hare and the tortoise are iterating. They're iterating over a sequence of numbers, and the next number in the sequence is kind of generated from the previous number by the application of this mathematical function f. So we will have here the hare and the tortoise starting out at the number n. Now our template told us that we have a while loop saying while the hare can jump forward 2 steps. In this particular example, is it ever possible that the hare can't jump forward 2 steps? In other words, whatever number the hare is at, is it ever possible that we can't apply f on it and then f again on it? We can always do it. We can always do it. So in that sense, this condition, hare dot next is not null and hare dot next not next is not null, is always going to evaluate to true. Since it is always going to evaluate to true, let's just write it as while true. What does this tell us? Within the body of the while loop, we have to write hare is hare dot next and tortoise is tortoise dot next. So we have to move the hare forward by 2 steps, and we're going to do that not by doing dot next as in a linked list. We will apply the function f 2 times. Likewise, we'll move the tortoise forward from whichever number it's at by applying the function f once on that number. And let's worry about how to implement f separately. So we keep doing this, and we know that this is going to end in a cycle. So that means there will be a point where the hare and the tortoise match. And when they match, if the value that they are at is a 1, that means the original number n must be a happy number, otherwise it's a sad number. So if the hare and the tortoise match, and this is a mathematical sequence, so there's no location here, we're talking about the plain numbers, the values of the numbers. If it's 1, then it's a happy number, otherwise it's a sad number. So we can just return whether either of their values is equal to 1. So how much time does this take? Well, we saw that for any practical integer value, right, which can fit into, let's say, 9 or 10 digits in our number system, any cycle can't be of length more than 800 or so. So that means accounting for the fact that so it's not necessary, by the way, that the first number you start out with is going to be part of the cycle. If you note here, 2 was not part of the final cycle we ended up in. 4 was the first node in that for the number in the cycle, and then we keep oscillating around that. But we know that this chain can't be more than 800 long before we end up at a cycle. So it's going to be around 800 long or maybe 1600 long. In either case, it's just going to be a constant time. It doesn't matter what the value of n is. For practical purposes, it's just going to be a constant. If we really wanted to be nitpicky and say that, well, our numbers can be as big as possible, then you have to look at how many digits there are in that number, which is going to be log base 10 of that number, right? The number of digits here, number of digits in n is going to be roughly log base 10 of n. And so if each of the digits was a 9, we would do 9 squared or 81, add up 81 as many times as the number of digits. So this would be roughly 81 times log n, right? Which is still order log n. And that would be the maximum length of this chain, before which we start seeing a cycle. So and then even if we allow for some delay with the hare and the tortoise, going around that circular track until the hare catches up with the tortoise, it's not going to add anything more than uh, log n more in uh, in complexity. So we can say the time complexity is roughly order log n. The auxiliary space used is obviously just a couple of variables, which is nothing, which is order 1. Any questions on this? Paul?
Hi, Omkar. How
Hi.
did you arrive at that log n complexity for time?
Well, because we are talking about the base 10 number system here.
Hmm.
So in base 10, if you are at 2 billion, right, whatever this is, let's say the number of digits here is k, right? What
Hmm.
is the maximum value that you can get if you used k digits? So the maximum value you would get is, if all of them were nines,
Hmm.
which is actually one less than 10 to the power k plus 1. Right? If you
Right.
had 9 digits, all of them are k's, that would just be one less than, 1 followed by 0 k's,
Correct. Correct.
right? Which is basically 10 to the power k actually, right? 10 to the power k minus 1.
Hmm.
So if the magnitude of the number, so if n is roughly of this magnitude, then we know that it has k digits. So how do we get k? If we are given n, how do we get k? We take log base 10 of both sides,
Hmm.
and we would get k is roughly log
Log.
n,
Okay.
log of n to the base 10, right? Take
Hmm.
log base 10 of both sides. So
Hmm.
if n is roughly 10 to the power k, k will be roughly log of n to the base 10.
Hmm. And how does that map to the time complexity for this? Because you are
Bec-
saying that the while loop would.
So we are saying that when we apply this function, whatever transformation we are applying,
Hmm.
uh, the value that we are going to get when we do that transformation on any n
Hmm.
is going to be at most 81 times the number of digits in that number.
Right.
And if the number of digits is log n,
Hmm.
that means we'll have roughly 80 times log n as the maximum possible value that any of these numbers can have.
Correct.
So even if each of these numbers was different, after looking at
All the
80
numbers.
after looking at 81 times log n numbers in this sequence,
Hmm.
by the pigeonhole principle, some number would start repeating.
Correct. Correct. Okay. Okay. Got it. Thank you, Omkar.
So that means the length of the chain up to the point where you actually have a cycle beginning is going to be at most log n. Right. So if
Yes.
you were to
Yes.
visualize, it like this, there is some chain up to the point where, so this is the point where So you go up to this point, right? All unique,
Mm.
and then some number starts repeating.
Correct.
So this length would be roughly order log n, right? 81 times log n. Okay, 81 is a relatively big factor, but considering the fact that in this problem n is at most 2 to the power 31, that means around 2 billion or so,
Mm.
right? Because 32 bits number of IP addresses are would be 4 billion. We know that.
Right. Mm.
So assuming only positive numbers, half of 4 billion would be around 2 billion. So uh, and 2 billion is in decimal, in base 10. In the base 10 number system, 2 billion would be 2 times 10 to the power 9. So it would have around 10 digits.
Mm.
10 digits means log n would be about 10
Right.
at most 10. So 81 times 10 would be around 810 or so.
Mm. Mm.
Okay. So whatever it is, 800 or whatever it is, uh, we'll have this, and then we might have some additional numbers in the sequence while the hare and the tortoise are, catching up with each other. Depending on how far they are,
Correct.
uh, we might have, when the tortoise enters the cycle, we might have to do a few more iterations before the
Mm.
hare catches up. So it's
Thank you,
overall it's
Omkar.
going to be order log n,
Yeah. Thank you, Omkar.
where n is the value of the number.
Yes.
Anuj,
Hey, so I understood most of it, but if you could go to the next screen and could once again explain that why the chain can never be more than 800 nodes longer?
because whatever value you start out with n here, all of these values are guaranteed to be less than or equal to 81 times log n to the base 10.
Okay, I understood this, but
That means guaranteed to be less than or equal to 810 or something. Yeah, go ahead.
yeah, so what I don't understand that I understand the part that we will eventually the values will eventually start to converge and we will come back, but uh, why can't it be like we end up on a value which is not present in the chain? Like, so you start applying function f on all these ends, but
Hmm.
once you start to converge, couldn't it be like you land up on some value which was not present to begin with in the chain?
So if you land up at one value that was there in the chain, from there on everything repeats, right? Because this function is not, it's deterministic. As soon
Hmm.
as you see a value that you have seen before, everything from there on is going to be repeated in
Okay,
exactly
so
that's.
mathematically, how can I prove that I would eventually land up back on this thing? Like in case of 100, I do understand that, but
Yeah, because
mathematically,
so if all of these values are guaranteed to be under 810, right? If you assume
hmm,
that all of these values are guaranteed to be under 810, that
hmm,
means after applying the function f 810 times, I should start seeing some value that I've seen before.
got it. So basically, what we are saying is that for all the valid integer values, there are only 810 unique sums which are possible.
Yeah. Now you can start outside that 810 value, right? You could start out with something close to 2 to the power 31 in magnitude, but in just one application of f, the very first application of f is going to bring down the next value drastically to
Hmm.
under 810, and then once you're there, then it's just going to keep, you know,
Yeah, yeah.
it'll
Okay.
get even smaller, and then within a very narrow range, it will keep, moving around. But then once you have applied it enough number of times, some number there is going to be repeated because you're within a very narrow band of values. So you can't just keep doing this forever,
Okay.
right? So it's like this common principle called pigeonhole principle in discrete math, where if you have like uh, k different pigeonholes and you see k plus 1 different pigeons, um, emerging from those pigeonholes, it's obvious that some pigeonhole had at least multiple pigeons. So here the pigeons are analogous to the numbers that we are generating by applying the f's, and the pigeonholes are like the values that we have under 810. Once you generate enough number of pigeons, it's clear that uh, multiple of them are going to map to the same value. And once that happens, everything repeats. Rahul?
So here, if you go back to the algorithm that's there,
Mm-hmm.
uh, the the algo that you have written for this.
Okay.
So here you're checking, you're first checking, here equal to tortoise, and then checking if here equal to 1.
Mm.
So there you'll always reach here equal to 1 before here equal to tortoise is there. So in terms of how many times you are calculating,
Yeah, I mean, I could have checked hair equal to 1, right? If hair is equal to 1, I could have, in fact, I think that's how I have it here. I could have checked hair equal to 1 and then exited.
Yeah.
Otherwise, when I catch up with the tortoise, I will return false.
Okay.
Right. So I'm just compressing that. Uh, so if hair reaches 1, obviously the tortoise will also eventually reach that 1. So yeah, you could say that the hare could reach 1 quite sooner. So we don't have to wait for the tortoise to reach
Sure.
1. We could immediately return. So that's certainly something you can do.
Yeah, and another thing, if you go by just the naive implementation of this, where we are not doing, where we are not, looking at here in tortoise, where we just, go and keep on calculating all these sums in a loop.
Hmm.
Won't it be better, from time complexity again? A bit
How?
better.
How?
Because as soon as you reach 1, you're returning it. You're not waiting.
Yeah, but that's assuming that the number is happy. It's like saying as soon as as I reach the end of the list, I know that there is no cycle. But what if the number is not happy? What if the list has a cycle? How would you know that I'm going to continue forever?
Yeah. So for that, we can just maintain a hash set out there and keep on adding our sums to the hash set. And
Yeah.
as soon as we encounter it again, that's where.
Yeah, the problem is that it would still be asymptotically, it would still be order log n. And in terms of auxiliary space, also now you would have to use log n space.
Yeah, space will be more. I agree. But we'll never be recalculating anything.
We'll never be you'll actually detect the first duplicate
Yep.
as soon as you generate the first duplicate. So so you gain in terms of time a
but
little, but you
lost in
lose out
space.
in terms of space. And what you gain in terms of time is just a constant factor. What you lose out in terms of space is not a constant factor. It's log n. So that's why overall this would be like the most optimal approach.
Again, going back, in terms of space, all we have lost is since maximum numbers of numbers, that can be there is around 810.
Yeah.
That's what we have lost.
So in general, you would lose around
Yeah.
log n if n is the magnitude of the number and it was allowed to be indefinitely large. Then
No. If even if your number is infinite, like it's 2 raised to the power 31 minus 1, like maximum integer possible. That's out there. Still, the maximum number of records that you will be storing in your hash set is going to be approximately 810.
Yeah, from practical standpoint, sure, but not from a theoretical standpoint. From a theoretical standpoint, when you're given an integer n as input, your input size is basically log n, right? Because log n to the base 2, because that's how much space is required to represent n in memory. So in this problem, when we say what should we measure time in terms of, we should measure time in terms of the input size. And the input size is actually not n, it is log n, which is the number of bits that are required to represent n, because that is the amount of memory that's given to us as input.
Great.
Now, when you say that I'm going to use log n space to store the hash table, it's like saying I'm using order of input size auxiliary space.
Got it.
Right? So it's actually significant in terms of the input size. Even though 800 might not look like a big value, but theoretically, it's significant because the input size is log n. So you have to, if you're using order log n space, that's like using order n space actually. It's just that n here is because the input size here is not n. N is just the integer that we're talking about. The representation of n is actually of size log n.
Yeah, got it. So essentially what you're saying, right now, because n is an integer, this number is 810, if n is like long or maybe some other fictitious new type of, data type out there, this can be very big.
Yeah, this can be very big. And, for practical purposes, even what you're saying should work. But, if you know this way of doing cycle detection, it has the advantage of being theoretically efficient as well. So might as well just use the same template. I haven't written the definition of this function, so let me write that also. Given an integer x, what is f of x supposed to return? Well, suppose the return value is, so we have to break x apart into each individual digit and add up the squares of that, right? So let's maintain a total counter which will track, which will keep a running sum of the squares of all the digits. Now, as long as x is not 0, we will try to break apart one digit at a time from x. So x mod 10 would be the rightmost digit of x. So if we square that, that's what we would add to the running total. And since we have accommodated that rightmost digit, we should reduce the value of x. Right, integer div. So we keep doing this until x becomes 0, and once we have chopped down the number to nothing, that means we've taken all the digits. Right, like hyenas, we've been plucking out each digit, tearing apart x into individual digits and squaring them and adding them to the total. So the value in this case would be sitting in that cumulative sum which we just returned. And that is what we plug in here, assuming that f is defined in this way. Heng Lee?
Yes. Yeah. I have one question. So for the recursion, what is space complexity, is that still like no again?
There is no recursion here.
No recursion here.
Yeah. We just have a two-level thing, right? When we say f of hair, what's happening is this is calculated, and then the return value for that is passed into another uh, function, like the same function one more time. So it's just a two-level thing. So if you look at the definition of f of x is not calling itself. So there's no recursion in that sense.
Okay, I got it. Thanks. So the time complexity is like O1.
Yeah. So I could have split this into two separate statements, right? Then it would have been even more clear. Hair is f of hair, and then I have another line saying hair is f of hair.